Hello everyone. Thank you very much, Marina, for your very kind introduction. First of all, I'm very honored to be at the first international workshop on computational information technologies for risk-informed systems. I'm Sorin Nistor. I'm a postdoctoral researcher in the Department of Computer Science from the University of Bundeswehr in Munich, and together with my colleagues and also with our friends from the Moldavian Academy of Science, we are going to present you today a concise review of AI-based solutions for mass casualty management. Before we are starting, it's important to mention that this work is based on a NATO project from Science for Peace program, and I listed here the key priorities that we are tackling from NATO through this project to emphasize the applied side of this project. Even though 3 out of 5 partners are coming from the computer science direction, we are having a really good combination with the applied side as well, with the University of Medicine and Pharmacy and with the Maritime Studies from University of Rijeka, Croatia. It's important now to start with some brief definitions for the applied field that we are tackling. So we are referring here to the response to disaster scenarios that result in mass casualty incidents, or called MCIs. And an MCI refers to multiple casualty situation that emergency medical services resources as personnel and equipment are overloaded because of dealing with a large amount of serious casualties. Those represent outlier events where immediate concerns is the mass casualty response. And of course, they are dynamic environments because they treat the threat might be or might still not be active. It depends on the kind of threat we are dealing, if it's a human disaster or if it's a hazard resulted by nature. We don't know if, for instance, if in case of an earthquake, now everything stopped and we can start saving the victims, or if it's terroristic attack and here the terroristic attack just stopped with that situation, or there are going to be some others ongoing. More specifically, we refer to the mass casualty management, which describes the process of attending the victims of MCI, with of course the aim of minimizing the casualties. And an optimal MCM should consider the 4 phases of any disaster cycle, like here mitigation, which where some of the devastating effects of the disaster can be reduced using many useful actions. This before the actual event happens. The second one is the planning, where all the plans and the practice is done. And here is important to check if those are faulty or if they are unworkable in realistic cases. The third one is the most important one, is the response phase. But an effective response phase cannot work with the other 3. And the last one is the recovery phase, where actually the rebuild and the reconstruction of the infrastructure starts. And I'm here emphasizing the response part, and I'm giving you some of the components of the response phase that are very important, like for instance consider activation, notification, initial response, the organization of command and scene assessment, search and rescue, and extraction, triage, and transportation. Now, just without going too much into the deepness of this picture, here is a hierarchy of the incident command system, and it's important to understand that the whole investigation or the whole response is led by the incident commander, and of course there are many other people within the staff, but we are not going to get now into the details. And it's important to see how the communication linkages in mass casualty management, where we have multiple agents like the hospital command, the evacuation officer, triage, medical field command. And what is important for us was to identify where the AI-based solutions can be applied in this middle area, where this solution has been found so far very useful or applied in practice, and which ones of them are the state of the art in these terms. Now, when introducing the tools, I'm going to start first of all with the traditional optimization techniques. And one notable work is the spatial decision support system introduced by Amram et al. In 2011, where the system considers some variables at the incident location, such as the near hospitals and their capacity and treatment specialization, in order to help the center commander make a decision. This system also integrates the raw network and the hospital information to estimate the certain driving times in seconds to the hospitals based on the pre-computed times. Later on, they introduce also the mass casualty patient allocation model, which can be used in two different ways. If you remember the disaster cycle, in the third phase, it can be used to transfer the real-time information concerning the casualty counts, hospital driving time, hospital bed capacity, to enable more effective management of the patient evacuation from one or more MCIs, and also in the second phase of the disaster cycle, where it can be used for training and planning, as it allows for simulation exercises for evacuation from an MCI. Another notable work is the combinatorial optimization model by employing a scheduling approach of Wilson et al., where the authors proposed a multi-objective optimization method that considers key factors in MCI, such as the health level of casualties, scene of incident, and appropriate hospitals for each victim. They proposed a framework based on flexible job shop problem that can be adapted to accommodate the unique characteristics of the combinatorial optimization problem. The next important work that is to be found is the such called severity adjustment victim evacuation, or the SAFE model, introduced by Dean and Nair. And this model focuses on the critical time period immediately following the onset of the MCI, and it considers how to effectively evacuate the victims to the different hospitals, and this by using the RPM score, which includes the respiratory rate, pulse rate, and motor response. The last from this category is the mathematical model based on resources constraint for triage operations, introduced by Kamali et al., where the most important part, this model show how to scale the disaster in availability of the resources affects the outcome of the triage operations. The model analysis provided decision makers with optimal prioritization policies to maximize the expected number of survivors. And what is the most important, this model works with minimal data requirements to the specificality of the number of the casualties in each category, the service time, and the number of the severe available. Now, from the reinforcement learning based optimization techniques, we have the first one of Quen et al. That claim to have a better response to victims' requests during the disaster, and this based on the Twitter data collected Hurricane Harvey in 2017. They proposed a novel algorithm, which is one of the first approaches to deal with the large-scale disaster rescue problem using multi-agent reinforcement learning in social network data. These authors designed a heuristic multi-agent reinforcement learning scheduling approach that can handle multiple volunteers to rescue disaster victims quickly and effectively. This model can respond to dynamic requests and maximize performance over time and space in a limited resources and large-scale areas conditions. Now, the second notable work that we have here is the deep score network to deal with the dynamic factors in ambulance stations, introduced by G et al., where they create an effective model based on deep learning techniques used for redeploying the ambulances to minimize the transportation time and increase their survival rate. Whenever an ambulance is available, it is needed to redeploy to a proper ambulance station, such as that it can pick up the next patient easier. These authors proposed a deep neural network called Deep Score Network to deal with the dynamic factors in ambulance stations. They converted them into one score on which they can dynamically redeploy a free ambulance with the highest score. The deep score network was trained using a policy gradient algorithm in deep reinforcement learning in order to minimize the pickup time for patients. The data was collected from the EMS system in city of Tianjin, China, which consists of EMS request records, road networks, ambulance stations, and hospital. This is the first paper that proposed a deep neural network for redeploying ambulance dynamically based on reinforcement learning. Now, another notable work is the Mobi Rescue, or the mobility-based rescue team dispatch system, introduced very recent by Yan et al. To help to maximize the number of responses to rescue requests, minimizing the driving time and the number of units. The scenario of this research is under flooding disaster and use of the city-scale human mobility data set for the Hurricane Florence. Because of this different impact of the flood disaster in different regions and people's movement also affected, the rescue team's driving routes should be adaptively adjusted. They used a super vector machine to predict the distribution of potential requests on each road segment. Based on this distribution, a reinforcement learning method to deal with the mentioned problem. They used dataset recording during 15 days in the Charlotte city of North Carolina, which consists of the mobility of 8,590 people. The last category we are tackling regarding the AI-based solution is for the transportation congestion detection, because during the casualty transportation process in MCIs, an important task needed to consider is the traffic state detection. In emergency situation, ambulances cannot transport casualties to hospital timely to receive further treatment if they are not being victim of a traffic jam or blocked ways, especially in urban cities or destroyed areas. And for this, we are mentioning one of the notable works in this direction of the Cauthery in 2018 on dynamic control system applied in Dhaka in India, where they measured the traffic density from real-time videos and image processing. The traffic density of specific lane is estimated by detecting the cars and counting the number of cars entering and leaving the lane with 2 cameras. The adaptive learning method is the mixture of Gaussian method was employed to identify and count the number of cars in the lane. Once detecting and the counting tasks have been done, the data is set to the traffic intersections hubs for estimating the lane density. Now it's important to also consider in computer vision the unmanned aerial vehicles and what we can do with them, because they have a high advantage of high probability and they are used popularly and effectively in computer vision. In casualty transportation, speed, density, and volume are the most crucial parameters for the commander to give tactical decisions in disaster response. So, authors like Key et al. In 2018, they introduced a complete framework for estimating traffic flow parameters for UAV videos. This framework consists of 4 stages, 2 for vehicle detection and the other 2 for the traffic flow parameters. Interesting also for Do et al. In 2018 they introduced the UAV benchmarking, which consists in is part of 3 tasks on detection, single object tracking, and the multiple object tracking tasks. The benchmarking aims to solve high density, small object, camera motion, and real-time issues of UAV platform. The authors focused in vehicles and datasets of more than 100 video sequences selected from 10 hours of video taken by UAV in complex scenarios. The weather conditions, flying attitude, camera view, vehicle category, vehicle occlusion, and out of the view are considered. Now, UAV and a combination UAV platform with AI proposed to solve the traffic congestion recognition problem is introduced by Jian et al. By using the UAVs, the traffic monitors can see the traffic scenes from all angles, receive data faster and cheaper, And this platform can be applied for casualty transportation to powerfully treat patients timely when a mass casualty happens. Now, a novel count vehicle approach based on expressway videos was introduced by Meng et al. Using a new vehicle correlation method algorithm for tracking to deal with the trajectory point instability problem and solve interruption and uneven problems, and counting the multiple targets of the moving in the different directions with different types of vehicles with a new multi-vehicle counting method. The framework can work effectively based on video sequences under different climatic conditions. This work can be used as a basis for building a decision support system in a traffic state detection during casualty transportation in MCI. When applying these AI-based solutions, we actually identified the really important challenge is the one for the emergency response vehicle to identify what kind of road blockage is that. If it's a road blockage created by a traffic jam, there should not be a problem with the lights and with the emergency sound on, but if it's due to a natural hazard, this is going to be way much difficult to consider that road as being still a part of the route for the emergency response. And with this, please write me in chat in case you have any questions, or at sorin.nistor@unibevet.de. And with that, I'm thanking you very much for your attention.